much for that kind introduction, for the possibility to speak here at the Hausdorff Center, which is a true honor. Okay, in fact, I have never presented on that blackboard anything, perhaps on slides, something. So I will not give you a technical talk, but a talk with a focus on an overview of the subject of modeling and its relevance for the mathematical side of it. I'm still an applied mathematician, so I want to do mathematics. And Dr. Haug asked me to talk about the Cosserat model especially. And so I will give you a short introduction to the Cosserat model, how I view it. There is a lot of debate about the Cosserat model, what it can do or what it can't do, and the mathematical aspects of the Cosserat model. Then we will touch also shell theory a little bit, perhaps beam theory. I will allow myself, if I have enough time, to do some linearization, because in the linearized setting you have some other mathematical challenges which arise and which could be interesting. And then my time will be basically over, I guess. So let's start with the Cosserat model. And the Cosserat model is basically a nonlinear model. Nonlinear Cosserat model. The Cosserat were French brothers, and they produced a big book in French around 1909, in which they exposed a generalized continuum theory. And nonlinear, there is not one linear equation in their book. Of course, there exists linear Cosserat model. I will show you this not in a minute, but in a moment. And people rediscovered the Cosserat model in the 1950s around. And in that time, the computer was still not there. You wanted to calculate something. And in order to calculate, you have to go back to the linearized setting. That is how I try to understand what happened. And they were very much doing research into the linearized Cosserat model. And only in the late 80s and then 2000s, people rediscovered in a way the nonlinear Cosserat model and tried to look at its properties. But we are going the original way. Back to the Cosserats. I studied the book in French in detail because at one conference someone told me, oh, I cannot understand, I don't even find the tensors, the objects which we now use. And I told him, well, you didn't look close enough. On page 42 that is this tensor, on page 43 that is this tensor, of course in French. And in indices, let's say in components, not in indices. So what's this Cosserat model? Imagine you have a body. And classically, you would consider, in nonlinear elasticity, you would consider the deformation of the body by a deformation phi occurring due to applied loads of the body. So the phi is a mapping of that domain to R3. And for the following, I assume every smoothness I need to do my slide mathematics. So the phi is smooth. That means each point here is mapped to another point, and if you have two points neighboring each other, they are mapped to neighboring points because the phi will be continuous. And you know the setting of nonlinear elasticity, and the Cosserats knew that very well. They mastered the subject completely. Today the subject is easily introduced, but not completely just that you minimize an energy depending on the deformation gradient. We call this a deformation gradient, but in fact it's a Fréchet derivative of phi. So that there is no problem in whether it's a transpose or not. I once had to spend some weeks to understand that a certain calculation didn't go because the Russians are using a transpose gradient. But the d phi is unique. So you minimize this with respect to some boundary conditions. I'm not giving body forces now. That is classical nonlinear elasticity. And everything hinges now on finding sufficiently general energy functions so that that variational problem makes sense as a minimizer, whatever. And the Cosserats immediately extended the problem by considering small domains around a material point, and now assuming that these domains here can rotate. And they are mapped together with phi, but not only according to phi, because of course I can map that quadrangle with phi, and that will be an affine quadrangle after all, or whatever. But that this rectangle here has its own life, can do something independent of the material point here. That means, let's make a cross in it. Let's make a cross, just one cross, so that is your initial cross. And now you attach this cross here, but it has its own life. That is, you have a cross here, a deformed, let's make an arrow here, so that arrow has been done here, and that cross is getting something like that. So you have the possibility that the crosses here in the body interact with each other, and they interact, of course, with the deformation phi. The mapping of the crosses is, of course, a rotation matrix. You have an initial, let's say initially you have the straight crosses coordinated, and now you map them to rotated crosses. It's 3D, but I cannot draw it. So you have a map R, which attaches to each point x in omega, omega in R3, which attaches to each point a rotation matrix, SO3. Special orthogonal matrices. So we should augment our variational principle with the possibility to come up with rotations. So let's say I should have d phi and r. Let's start here. And now the idea of the Cosserats, this I don't remember whether, well, they were variational. So they knew we want to minimize. We want to minimize the new energy, now of course not only with respect to phi, but also with respect to the rotations. So you have, in nonlinear elasticity, the W cannot be convex in d phi, for some reason that I can explain to you another time. And here this W will already be non-convex, however, because of invariance conditions that you have to apply, which I explain in a minute, the whole problem is anyway nonlinear. But now let's look what happens if I have just a rotation here and I minimize with respect to rotation, if there is no other contribution in the energy. Then the Euler-Lagrange equations for that, because R doesn't have a higher gradient for the moment, means that the rotations can be minimized out, condensed out directly, and it will be a nonlinear algebraic equations connecting the rotation to the deformation gradient d phi at the specific point. That is, the rotations here would only interact with the deformation, but not interact with themselves to say that, okay, here I have rotated to the left, here I have rotated to the right, I should somehow pay energy to do that. And that effect is still missing. How do I connect rotations? To say that I want to see differences in homogeneities, well, I have to give it a gradient. I want to measure in addition gradients, let's say dr. Now, of course, the d phi, this is a 3×3 matrix, the Jacobian, the Frechet derivative. R is a matrix, but an orthogonal matrix, and dr means all first derivative of 9 components in R. Because the rotation for the moment is just a matrix, which has a side condition to being orthogonal, but otherwise it's just all partial derivatives. So that is a tensor, an object with 27 entries. It's just dk rij. Ij for a rotation and all partial derivatives. 27 entries. But for us, the special format of that tensor is not important. The only important thing is that we want to control the full gradient somehow. Yeah? For us, it doesn't make sense to say one direction is controlled, the other direction is not controlled. We want to have the full gradient. And for example, I could write down as a measure, I could write down dr squared. That means all components, all partial derivatives of all components of R squared and summed. Big object, but a simple object. Okay, so now the business about the model is, why would you do that? Why did the Cosserats try to do that? That allows you to act on these rotations independently if you want. For example, with a magnet, you can put moments into the material, and you could try to say that this is a kind of thing that I can try to turn to the left, this I turn to the right, and still the material should react and produce some deformation. So you have a lot of ideas where this can come from. That would be too applied, and we could discuss the engineering science. Now I want to discuss how should we choose the W now, so that this makes some sense. The first observation is, yes, I take the Giotto box. If this is your body and you rotate it, there is no change of energy. The rotation, this is important. We have now several rotations in the business. We have the rotations here which are attached to each individual point. That is, you have a rotation field living in the deformed configuration, and you have one rotation which is rotating the whole body. So let's look what's happening with one rotation. So when we look at the deformation, one rotation is doing the following. d phi is going to, and now I should use another sign, q, and I make a bar over the q because it should be a constant rotation. That is what I'm now doing with the Giotto box. Is doing that. If I look at d phi and now I'm rotating that body, it's q times d phi. If I have here a rotation locally, that rotation will be once rotated also with that q. So the r turns into qr. And if I have a derivative dr, it turns to just q times dr, because the q is homogeneous. It's just going out. And we need to make sure that, so this is frame indifference, we call it indifferent of frame indifferent or objective. This is just the nomenclatura of the theory. That the energy that you use, the energy density that you use, must be invariant under that transformation. So I need to require that W of d phi r dr is equal to q d phi q r and q dr. And this for all possible homogeneous q, for all q in SO3. And now there is the first reduction of, I don't call it a theorem, I don't call it a theorem, it's reduction observation. That you can specify that you are, okay, you have to remember the polar decomposition. Polar decomposition. That is, if you have an invertible 3 by 3 or n by n, but in my case everything is 3 by 3, F, matrix F, and the F is always taking the role of the d phi. I will not write anymore the d phi, it's F, capital F. I can decompose any 3 by 3 matrix invertible in a unique way into R times U, and the R is SO3, and U is a member of positive definite matrices where this is my notation for a positive definite matrix. You can calculate U as the square root of F transpose F, the matrix square root. And so you have this polar decomposition, and I will also tell you something more about the polar decomposition later on, because that reappears every other moment. But it means that my energy, I can look at the energy like that, F, R, and here dr must be the same as Q, F, Q, R, Q, dr for all Q bar. I can insert the polar decomposition of F and choose at will Q bar to be R transposed. So choose Q bar equal to R transpose, and this is a permitted choice to do that. So you get W of R transposed F, then R transposed R, and then R transposed dr. But now this is a bad notation, because this is not the same rotation as that one, so I should perhaps give it a tilde here, just for that argument. Here, and this here, Q, and now this R transpose, that was the R transpose tilde here, this is cancelling, this is the identity, after all that was the Q, so this is R tilde, this is R tilde. And you get the following reduction. This R tilde transposed F is in fact the U here. And then I have R transposed dr tilde. So in the end, you get a reduction. So this F, this is a polar decomposition, yeah. But I could write it like that, but I can take any other rotation here to do the same trick. And that means if I take just another rotation, I can just write now, following the same steps, I can write, let me call the Cosserat rotation, because now I see it, it should have a bar everywhere. Sorry, bar, because for me the bar means this is not the rotation from the polar decomposition. That is just the nasty thing, you have too many rotations here. That one, I hope this makes clear. So I can get R transposed F here. I can get here a 1. I kill this rotation by choosing that R transposed in the invariance condition, and I get here R bar transposed dr. And this is now a possible representation. I can represent each elastic energy of the Cosserat model based on these two tensors, these two objects. And in fact, this tensor is called the first Cosserat deformation tensor. Tensor because it's a 3x3 matrix, it's called like that. And this is the second Cosserat deformation tensor.
So, question.
Yeah.
I'm confused. I thought Q was global in your argument, but then now R is a local variable.
Yeah, that means you have here a dependence on x.
Yeah.
So, but you can do that in every point x. That means you reduce it once, assuming everything is homogeneous. You can do that step. And then you put it together, you allow this x dependence, and then everything is, if this is now in x, okay, the f is in x, the rotation is also in x, you can choose just that rotation which you need in that point to make that argument, and that's it.
Okay.
Yeah, it's a good observation, in fact. You can get a little bit confused about that. Anyway, we can, by analogy with the polar decomposition, we call this guy here U bar. U bar is, because you can then write U bar equals to R bar F. Should be okay. No, U bar equals to R transposed. Like that. Yeah. And the other one, okay, the second Cosserat deformation tensor. And now what people did, and the Cosserat didn't do it, because in that big book, a big French book of more than 350 pages or so, there is not one constitutive prescription, meaning specify to me the energy. What they did was giving this argument in components, and to say that everything can be reduced to the arguments of that guy, combined with the arguments of that tensor, and then it's up to you or whatever to make up an energy. And so now, in order to be sufficiently specific, we choose the most simple energy that we can imagine, having in mind that still the model is automatically nonlinear, because we have used geometrically nonlinear objects, geometrically exact objects. So the best thing that you can think of is a quadratic energy. Choose quadratic energies. And by the way, no, this is now coming. I am not considering anisotropy. Anisotropy means a preferred direction in the material. That will not be treated here, because that is another level of complexification. So everything will be isotropic, and so you can think of the most simple quadratic expression in these two objects being isotropic. This is still a large family, because you could think of a direct combination of that tensor and that tensor being put together in a scalar product. This I will also exclude, so I will look at the most simple isotropic expression where the effects are separated. Okay, so isotropy plus separated effects gives you that the W is a function, and I already give you the final result. The Frobenius norm of U bar minus the identity, no, that is wrong. The symmetric part of U bar minus the identity plus the skew symmetric part of U bar minus the identity plus the trace This is for the first part. We agreed to use a quadratic form in that object. This guy here, look at the polar decomposition. If I put the rotation to the other side, U is this tensor. It turns out it's this tensor, and that is symmetric. This is symmetric. But if I have a free rotation, that bar means this is a Cosserat free rotation, this object here, the U bar, is not symmetric anymore. And therefore you can split your 3x3 matrix into a symmetric and antisymmetric part and a trace part. And that gives you the whole possibility for terms in U bar, and I have added one condition here. At the identity, if nothing happens, I want to have zero energy for a quadratic energy. That is the identity tensor, 3x3. Now this is the first part, and the second part I want to be easy. I just add dr. I could add r, I should use r bar transposed dr squared. Meaning all entries of that object squared and summed. Because to come up with something that makes sense physically in a more detailed way of that higher order term is very difficult. So it's enough to say that we have a control of derivatives of the rotations, and because there is a Frobenius norm here, in fact this R bar is not seen, it's factoring out immediately. I made the argument that it should depend on that object, but if I'm writing that simple expression, I can kill the R bar. It's just a dr squared. Okay, and now we have to think about the parameters which go in front of that term. For dimensional consistency of the energy and the equation in the end, you have to give it a mu. Mu is not necessarily here, it's just for the dimensional consistency, and a length scale. A length scale. So this LC has a dimension of a length, and because here I have a derivative of something which is without length, the rotation itself, but the derivative has a length, it must, over the length it must be compensated by an LC square. Okay, and this LC square, it will, so what are the terms doing? We have a coupling between deformations and rotations here, so that if the cross it's rotating, doing what it has to do, it's rotating, and it looks at what locally the deformation did at that point, and the interaction of the crosses themselves is encoded by the, we call it curvature energy. Curvature energy comes from the shell theory, where this term is typically coming where the shell curvature rests. So this is curvature energy, and the first term would be the strain energy. Okay, now what can be said mathematically about that problem?
I have a quick question, perhaps also a very naive one. So what is the interpretation of this trace term? So you have this symmetric and antisymmetric, why do you still need the trace term?
In fact, a much better interpretation would be to write something in the determinant here. In linear elasticity, the trace term is coming from the volumetric deformation. In the nonlinear world, and we are completely nonlinear here, geometrically nonlinear, a better way would be to say that this should depend, if it's connected to the volumetric deformations, it should be connected to the determinant of f, and the rotation would even factor out. Okay, I should, for example, write here, and that doesn't really complexify the problem. I can write here that u bar and the logarithm of it, for example, squared. The linearized behavior of that guy is this guy, but the advantage of that guy is when you look at what r bar of u bar, what it is, the determinant doesn't see the rotation. It would be a term which only sees the volumetric expansion of the underlying continuum via phi. So from a modeling perspective, that would be better. That can also be treated, but I want to say that this is the only quadratic energy that I can write down, and then it has this expression here.
Yeah, perfect, thank you.
Okay, so I observed that model was there, and now about the mathematics of it. Let's try to see what conditions we have for existence of minimizers. Of course, this is something that the Cosserats didn't do. That was then up to me around 2002 or 3 to look at it. Oh, just no one looked at it, and when you try your luck. So of course I assume that you know a little bit of functional analysis, Hilbert spaces and so on, and it will not be too technical, just to see what we can expect. First of all, the trace term doesn't
I'm sorry, I also have a very basic question about this strain energy. Usually in continuum mechanics there's this Euler-Lagrange strain tensor, right? That is
No, there are many strain tensors in nonlinear elasticity.
I'm just wondering how is it that this one is the right one to use, or is it that you say that this is the most simple one that you...
For the moment, take it as the most simple one. We can have other combinations, other energies. I'm not talking about now about the Euler-Lagrange equations. The Euler-Lagrange equations, just to remember it to you, we have a two-field problem. We have phi and rotations. So we have to take two variations. The first variation with respect to phi is easy as usual, but the second variation has to be taken with respect to rotations. And there you have to be, of course, careful. And then you get a system, a coupled system of automatically nonlinear equations because you are on the rotation manifold. But this, for the moment, we want to forget. We want to make statements about existence, not, of course, about uniqueness, even if the strain energy would be convex in the relevant terms here, because the underlying variables are non-convex. And what I want to say is we can forget about the trace term because it doesn't add anything to the argument. Okay? So we look only at Sym R transposed. And now I'm writing it down as it is written, d phi plus mu c q of R transpose d phi minus 1. Trace is absent plus, I forget ULC squared, that doesn't matter the concrete value, plus the derivatives of R. And we want to minimize this with respect to phi and R bar, yeah, and try to make sense what we should expect. So the good spaces, it turns out, is that your deformation phi will be a function in H1. Because we expect to have a control of d phi in L2. We have to see under which conditions we will have that. And we expect, but this is no expectation, we have it, the R bar is also in H1 with values in SO3. Why is this? This is automatically true for the theory because we control all derivatives of the rotations. And now this is a nice feature of orthogonal matrices. If you consider their Frobenius norm, it's bounded, it's square root of 3. This is not true for infinitesimal rotations. Infinitesimal rotations are skew-symmetric matrices and can be arbitrarily large. The rotations, the orthogonal matrices, are all automatically bounded, and that means we have a control of the derivatives, we have an L infinity bound of the rotations, and that means together, so we have here dr in L2, that's coming from the energy term, and we have r in L infinity automatically, and that means we can expect that r bar is in H1. Okay, now let's see under which conditions we will have a control of the H1 norm of phi. So the first condition, and that is a case which I don't like very much. Let's say mu c is positive. If mu c is positive and that mu c has a name, it's called the Cosserat couple modulus. Cosserat couple modulus. Of course, these moduli, like here the shear modulus, so to speak, and the Cosserat couple modulus, they should be non-negative. Non-negative, but not automatically positive. Of course, I will assume that mu is positive, but whether this mu c is positive or not, we have to discuss. So the first case is positive Cosserat couple modulus. Because you can express any 3x3 matrix in the Frobenius norm as sym x plus qx, because sym and skew are orthogonal in the scalar product which goes with it, I can just take the smallest number here. I can estimate these two terms versus the smallest number, the smaller number of mu and mu c against sym and skew. That means I'm here, and then I can put it together. I'm here, so I get minimum, the energy, let's call it the energy here, E is bigger than the minimum of mu and mu c times both terms together, and both terms together are just the norm. So this is R transpose F minus the identity squared plus dr, that is not changed. And in fact I don't need dr now. And now I observe that this is now a positive number, R transpose F minus identity. I can write this out, what it means. Is R transpose F squared minus 2 scalar product R transpose F minus 1 with 1. Wait a minute. That is coming 2 times. I'm already losing my concentration. I have to do it by hand. R transpose F minus identity, R transpose F minus identity. This is just written out, the square. So I have what I noted, R transpose F with R transpose F. I have this term with this term with this, and I have it 2 times, so minus 2 times R transpose F identity, and 2 times the identity itself is plus 1 1 with itself. So what do you see here? This is 3. This is what it is, and this is the length of a vector is invariant under rotation. So this is just F. So I have here F squared minus 2 times F times rotation. I just use properties of the scalar product to put the rotation on the other side, plus 3. And now when you look at this, and I don't need to go into more detail at that moment, you have a square on the derivative of phi. Here you have a linear term on the derivative of phi, while the rotation matrix is L infinity and a constant. And you control this term by the energy. So this is less than the energy, and that means you make a quadratic argument that controls the F square, the F in L2. That gives you a control in L2. Control of d phi in F equals to d phi in L2. And now what you have to observe is in linear elasticity you have to do a lot of effort, or a certain effort, in order to control the deformation, the displacement gradient. Namely, you need to use Korn's inequality, which is an integral inequality with boundary conditions. We didn't use here any integral inequality, and we didn't use any boundary conditions. The boundary conditions will only come into force when we want to come from d phi to phi, and we have to fix, of course, somewhere the body where we fix the deformation. So I have to have some Dirichlet boundary where you prescribe phi. But otherwise, nothing is needed. So we would at most need Poincaré's inequality to do that last step. So we see that for positive mu c, for positive Cosserat couple modulus, the problem is nearly trivial as far as this control is concerned, because we have now phi in H1, coercive uniform estimate, and rotation in H1, uniform estimate. And now let's see whether we can make an argument about minimizing sequences. Let's assume we have a minimizing sequence for the problem at hand. So that is convex because dr is converging weakly, but because you have the compact embedding, the rotations themselves converge towards rotations. So that term is fine along the sequence. Then you have here, you consider a sequence which, let's call that Rj. Rj converges strongly to R, and drj converges weakly to dr. So here you come up with V convergence, and this is a convex term, okay, for the limit inequality. Here you see that the rotations are converging strongly in L2, and d phi is converging weakly. That is a linear combination, that is a quadratic function, fine. And the same argument applies here. We will repeat that argument in a minute, but we see that this couldn't be more easier than that. Yeah? We have for nothing a uniform estimate, and because the energy was nicely quadratic, we can work even with these nonlinear combinations. Okay, that was the case, and I was really observing that for positive Cosserat couple modulus, this is not a challenging mathematical thing. Okay, let's look at what happens for zero Cosserat couple modulus, and the engineers would never have considered a zero Cosserat couple modulus, because for them this Cosserat couple modulus is a kind of spring between the deformation and the rotation. And of course, when you want to couple something, you need to have some coupling effect. And in the linear world, you would always need a positive Cosserat couple modulus. We will see that to make the model work. But in the nonlinear setting, we have the possibility to look at the other case, that mu c is 0. So the case mu c equal to 0. So that means this term is absent. We want to do the same argument as before. The only problem is that now we don't know immediately how to control d phi or phi with just this term here. So we have basically the object that we control is sim r transposed d phi, and I'm now adding squares, dependence of x, because this is getting important. Let's say, and the curvature term doesn't help me here. I have that control, I know I control this term, and I would like to come to something like phi in H1. For ease of exposition, it's clear that this minus identity doesn't do anything. That is just a lower order term in the end. So I will erase that term. And we have this guy. And it's good to think about that this is now a displacement, and here is a displacement. It's just you write down phi of x as x plus u of x. I can always write down deformation in terms of displacement. So if we have something like that, we would be done. Now you have to remember that there is Korn's inequality in linear elasticity. Korn's inequality, and what is it telling you? I take the most easy version. Fixed boundary conditions everywhere, compact supported functions, deformations, and I have the following inequality. I have the symmetric part of du, u in C0 infinity. I'm not looking at the details. Is estimating with the Korn's constant the full H1 norm of of U. And this is also 1906 or 1909, 6 or 9. There is a very interesting story about corn, but I don't have the time to tell you more about that at that moment.
So, question. So we're forgetting about the energy. So I mean, du does not have to be symmetric, of course, but we're saying that only the symmetric part matters.
Yes, because this symmetric part, now we have two objects here, sym there and sym there. This symmetrizer comes from frame indifference linearized. Linearized frame indifference means that your linear elastic energy only depends on sym du. And then you have to make sense that sym du alone, controlling the infinitesimal strain tensor, controls the u completely. And now, let's write this out. This is.
I feel like this shouldn't hold.
Okay, good point. Yes, exactly. This shouldn't hold. Thank you very much. This is just the essence. If you have an inequality which shouldn't hold, and it does, then it's getting interesting. Okay? So this is the inequality. I recall for the audience why it shouldn't hold. Because it doesn't hold locally. It cannot hold locally. You can have a skew-symmetric matrix, and you take the symmetric part of a skew-symmetric matrix. These skew-symmetric matrices I call A transpose equals to minus A. And of course, this can never be bigger than A. And there is no constant to do that. And yeah, there is no constant. I mean, not just a matrix field, okay? I can, for each matrix field that is 0, the symmetric part of a skew-symmetric field is 0, and that is not 0. I took it like that. So locally it's wrong, but when you apply boundary conditions, and the decisive thing is that your matrix is not just any matrix, but it's a gradient. And this is going into the direction of a gradient, of a rigidity result. This gradient structure here precludes that this comes into play. And that for this you have to do a little bit of work. But for example, you can see this easily, get an idea of what's behind that. If this is 0, you see the first thing in that kind of inequality that you have to check is, if this is 0, then the u should be 0. Okay, so we should check what the symmetric part of du equals 0 means, that du is locally a skew-symmetric matrix in SO3. SO3, small SO3 are the skew-symmetric matrices. And now this is a kind of most simple differential inclusion solves this problem. The gradient is a skew-symmetric matrix. It turns out that the only way for this to be possible is, this is equivalent to u being a constant skew-symmetric matrix plus a translation. But there you have to do something on PDEs, but it's easily done. And now you use, this is still possible, that would be an infinitesimal rotation. And now you have boundary conditions of place 0, you kill the two A's and B's and everything is 0. So that means this inequality can be true, and in fact it is true, but it's non-trivial. Now we have the problem that we have to consider R transposed du plus du transposed R. So we have a mixture with this R. Instead of just the symmetric part of du, we have at every point here a mixture. And the question, and there is no way to get the R outside, in the sense of I can have an estimate towards sym du. The R is effectively inside, and I don't get it outside locally. So I have to have a new integral inequality. And that's what we did in 2002-03. What I did in 2002-03. There is a constant which lets me estimate the u. Of course, for again u in C0 infinity, provided the R is smooth. provided R is smooth. So I have to specify what smooth means. Yeah, I will give you two sets of conditions because later on the theorem was refined. Okay, I can remove Korn stuff here, the classical Korn stuff. You just see that if this is true, this is a generalization of Korn's inequality, because if you set R equal to 1, you are back to your classical Korn's inequality. Or perhaps I should erase the other. Oh, I should do a little bit more exercise.
I might be wrong, but now could be time for a short break.
Yeah, just let me finish that argument.
Yeah.
Okay. What is the smoothness of R? So that was Neff 2002, and then Pompe defined it 2004 or so. The numbers may be a little bit different, but I don't need, so R is automatically in L infinity, because I could allow also non-rotation coefficients. That is now a rotation, but that is not the essence of the argument. So the should be in L infinity, and the curl of R, I'm not talking about the curl. The derivative of R should be in L4, very strange conditions, and the rotation should even be continuous up to the boundary. That was my condition, and Pompe just streamlined that R in. If you have rotations or matrices that are just continuous up to the boundary, then this inequality holds. We call this generalized Korn's inequality. Generalized Korn's inequality. And so if you have this now, you ask yourself, yeah, but do I have this kind of smoothness for the rotations to make that work? I should say that if this condition is not matched, then even for rotations we have counterexamples. Okay, so you need a certain level of smoothness for that matrix field which intervenes here, and the question is precisely how much smoothness do you need, because the proof somehow seems to indicate that R in L infinity, that R, now that should be considered as not a rotation matrix but an arbitrary matrix, that R away from 0, and the curl of R in L2 should be enough. What is the curl of R? R is a 3 by 3 matrix. I take the lines and I take the standard curl for a vector, that is the lines, and put it back into each line. Okay, and the question is whether this Korn's inequality does not hold under these conditions, because these conditions would be sufficient for our problem above. Why? I have written here curl of R. Now there is another, let me continue just that point. There is another inequality, but which is a local one, a rigidity lemma, or rigidity result. which tells you, and this is for rotations only, the curl, the matrix valued curl, estimates with a given constant, but I can calculate it, it's 1/2 or whatever, all entries of the derivatives of R. For R in O3, and this is even true for all dimensions. So the curl estimates the full gradient of a rotation field. So this should come as a surprise, because usually the curl is just not giving you all the derivatives, but only part of those derivative combinations with which are in curl. But here we have a non-linear side condition, the rotations, the R's are rotations. And then this holds, but this is local. No integration, no boundary conditions, just algebra. Lengthy algebra, you have to have some ideas. And so if you know that curl R is in L2, that means all the derivatives are in L2, and if all the derivatives are in L2, then the curl is in L2. This is just the same statement. So, for the problem at hand above with dr in squared controlled, we cannot show existence for mu c equal to 0. With this inequality, we would now have a control of u. Via u, we would have a control of phi. Then we would repeat the same argument, lower semi-continuity going to the limit, and the argument can work if I have enough smoothness here, I mean enough exponent here, so that I'm embedding into continuous rotations up to the boundary. And that means I'm in dimension 3, I need 3 plus epsilon. If mu c is 0. I don't say that this is optimal. I suppose that it's just a square that I can take, but it depends on what I can show here. And this result tells me that I should have smooth rotations up to the boundary, and the embedding of the derivatives of R to that exponent, that just gives me an embedding into smooth functions up to the boundary. So the message for that part is mu c positive, the result is trivial. We didn't do anything, we had no problem in estimating everything uniformly. If mu c is 0, the problem gets really interesting, because we need a new inequality, a new Korn's inequality of that type. And this inequality depends on how nasty the rotations behave from point to point. And I have a result up to the boundary continuous, but the application that I had in mind previously would rather use this, and somehow the proof indicates that this should be correct. The counterexamples that we have are not counterexamples to that. They are just counterexamples that just an infinity alone, rotations alone, don't suffice. Okay, and so we have understood the non-trivial Cosserat model, let's say, appears for mu c equals to 0, and of course I can somehow modify it now. I can say that I have my classical term, dr squared. It's a leading term, and I can just add a little bit of that term, which is a little bit extra control, in order to make up for the missing control of mu c. The mu c is replacing all that stuff with just I'm fine. And the mu c equal to 0 sees that, oh, okay, it makes a difference whether your rotation field is not smoothly distributed. And that for me makes more sense. You cannot expect that, or I wouldn't expect that a theorem is well posed if I can locally rearrange the rotation at will and still everything works fine. That doesn't make sense. And so the mu c is seeing this case, and we need a new inequality. So for me, this is the business of nonlinear Cosserat elasticity. Yeah, two fields, phi and rotation r, coupled through these terms, and you can then check what your Cosserat couple modulus is doing, and depending on that modulus, the engineers would always take a positive value. Everything works trivially, even simpler than linear elasticity. We don't need Korn. But in the case of mu c equal to 0, it gets interesting. And we have done numerical simulations. It's very, very interesting what's happening with mu c equal to 0, a much much more vivid behavior, and you can manage to fit it to experiments much better for some cases. Okay, this for the nonlinear Cosserat model.